Today, we will be looking at the effects of steady-state exercise on the body systems. To begin, steady-state exercise is pretty straightforward and is exercising at a constant pace for a period of time. A more technical definition is when the lactic acid removal is occurring at the same pace as the lactic acid production. Some examples of steady-state exercise is running or aquarobics. You can click on this link to view a video. In this video, we will look at the effects of steady-state exercise on 4 body systems. The first one is the cardiovascular system. There are quite a few things that happen to this body system that affect us. First, we have an increase in heart rate. As you probably know, when we start to exercise, our heart rate will increase. It will continue to increase until we reach the requirements of our workout and then plateau or flatten out because we are working at a constant pace. Let us look at this graph. First, we can see a slight increase in our heart rate and then it flattens out. We will also have an increase in our stroke volume. From previous lessons, we know that this is the amount of blood volume pumped during a heartbeat. This happens because we have an increased venous return. This is increased blood volume that stretches the cardiac muscles. The stretching makes the heart contract more forcibly, causing more blood to be pumped during each contraction, which increases stroke volume. This is known as Starling's law. We will also have an increase in our cardiac output. This is the amount of blood pumped in 1 minute. Due to an increase in our heart rate and stroke volume, we also get an increase in our cardiac output because more blood is required to supply oxygen to the muscles in action. Our heart is beating harder and faster. Thermoregulation. This is the body's ability to maintain a constant temperature. A few minutes into our exercise, our body starts to get hot, and the cardiovascular systems help us to get rid of that excess heat. The heat is lost through sweating and dilation of the blood vessels, known as vasodilation. As sweat evaporates from the skin, it also cools down the blood as it travels through the vessels close to the skin. Vasoconstriction also takes place around the organs so that more blood can be sent to the muscles. Lastly, we have an increase in blood pressure. The systolic pressure will increase because heart increases the force of its beats and the amount of pressure it exerts. Our diastolic pressure stays the same because the recovery pressure of the heart after it contracts stays the same. The second system we will look at is the respiratory system. There are 3 responses that happen to this body system that affect us. The first is an increase in breathing rate or breathing frequency. This increases to meet the demands of exercise to remove carbon dioxide in the body and supply the muscles with oxygen. Looking at the graph, it peaks for the first few minutes and then levels out to remain the same throughout exercise. The second response is an increase in tidal volume. This is the amount of air you can take in one inhalation. Our tidal volume increases because this is an increase in the depth of breath. We are essentially taking in bigger breaths of oxygen. And lastly, our oxygen uptake. This can be shown on the oxygen dissociation curve, which is a graph that shows the percentage saturation of hemoglobin and variable partial pressures of oxygen. Oxygen binds to hemoglobin from places with high oxygen and brings it to the muscle cells that have a low concentration of oxygen. Our CO2 levels and our pH levels can shift this curve either to the right or the left, which is known as the Bohr effect. Our blood becomes acidic when there is too much oxygen, which means there is a decrease in pH shifts. This shifts the curve to the right. In the lungs, there is a low pressure of carbon dioxide and low pH levels, would shift the curve to the left to enhance oxygen uptake. Our temperature also affects our oxygen uptake. If our body increases temperature, it shifts the curves to the right, and if the temperature decreases, it shifts the curve to the left. The third body system is the neuromuscular system. There are two things that happen to our neuromuscular system that affect us. The first is pliability or flexibility. As we start to exercise, our body starts to get warm, and so do our muscles. This allows us to become more pliable or flexible. Here we can see this girl is not as flexible before exercise, but after exercise, as our muscles get warm, you can see she's more flexible. This happens to prevent injury, such as pulling muscles. We also get an increase of neural transmission. As muscles warm up, the rate of the nervous impulse increases as the heat increases the speed of the transmission. This means that our reaction times will get faster. Our aerobic system is responsible for producing most of the energy supplied to our body, known as ATP. It is done through a process called aerobic glycolysis. Glycogen from our body is broken down into glucose using 2 ATPs, which is then broken down into pyruvate, giving us a net ATP of 2. Pyruvate is then broken down into lactic acid because there is a lack of oxygen present. This is known as anaerobic glycolysis. However, if there is oxygen present, pyruvate is then broken down into acetyl coenzyme and then enters a series of reactions called the Krebs cycle. Pyruvate combines with the coenzyme A to form acetyl-CoA, producing ATP, hydrogen, and carbon dioxide. This produces 2 ATP. The hydrogen atoms from the Krebs cycle enter the electron transport chain, which combined with oxygen produces a lot of ATP, helping us perform low-intensity exercise such as running for 30 minutes. In the electron transport chain, 34 ATPs are produced. This whole process takes place in the mitochondria of cells. The large folds known as cristae create a large surface for ATP production. This is a corrections page where I'll be adding a few bits of information to this PowerPoint. The first is the analysis of the cardiovascular system. All the responses that were mentioned on the cardiovascular slide happen within our bodies so that we can get rid of carbon dioxide and supply more oxygen to our working muscles. Our stroke volume increases and heart rate increases, automatically increasing our cardiac output. These increases happen so that oxygen can get into our muscles and keep them going. Thermoregulation happens so that vasoconstriction and vasodilation can send blood to where it is most needed around the body. The second correction will be for the neuromuscular system. For the transmission of neural impulses, we can test this by doing a reaction time test on a laptop, or we can simply do the ruler drop test, where someone drops a ruler between your thumb and index finger and you catch it and you measure the distance. The third would be the oxygen dissociation curve. This graph here shows the percentage saturation of hemoglobin at various partial pressures within our body. Oxygen binds to hemoglobin from places with high oxygen and brings it to the muscle cells that have a low concentration of oxygen. If we look at the graph, the tip of the graph has a high concentration of oxygen, which can be found in places like our lung. At the bottom of the graph, where the curve starts, is where there's a low oxygen pressure or saturation, for example, in our muscles. Our carbon dioxide and pH levels can shift the curve either to the right or the left, which is known as the Bohr effect. High levels of carbon dioxide increases the acidity of the blood. This shifts the curve to the right so that more oxygen can be delivered to the muscles that are acidic and keep us working aerobically to stop lactic acid production. In the lungs, there is a low partial pressure of carbon dioxide and low pH levels, which shift the curve to the left so that more oxygen can be picked up by hemoglobin and dropped to our muscles. The same thing happens with temperature. When our body has a slight increase in temperature, the curve shifts to the right so our body can send more oxygen to our warm muscles. When our temperature decreases, our core will slightly be cooler so hemoglobin can attract even more oxygen so that it can be delivered to our working muscles, causing the curve to shift to the left.